use this modified wheelchair, and we use also robotics to investigate human motor control, like this is supposed to illustrate. So a bit about myself. So I did study at ETH in Switzerland. After I was for the postdoc in Canada, in Japan, and in USA. After I was 5 years in Singapore at NUS, and I'm now for 10 years in the UK at Imperial College. And these are some of the main collaborators also for the work presented here. So my main interest is human-machine interaction. So human-machine interaction, so for that you need all kind of fields to investigate that. So robotics, control, neuroscience, psychology, and physiology. And so on the one hand, we have investigation of human motor control, so with experiments, and then we have modeling. And when there is something we do not understand, we go to modeling, and then we have questions, and we go back to do experiment to test the hypothesis. We have application, like, for example, right now we have quite a few projects on lower limb exoskeleton, training of microsurgery that we had some time ago, this brain control wheelchair that we did 10 years ago, so it's an old project now, just to illustrate some of the direction we go to. Okay, so now let's go to impedance control and learning. So this will be the main topics of today. So I have a few questions. So first, why do we need impedance control? And second, what is impedance? And I guess you had already this in previous day, and you know anyway. So impedance is a formalization of the dynamic interaction of contact. And because human or robots have to have contact, physical contact to act on the world, this is something fundamental. It's totally, it's very important to be able to characterize the interaction with the environment, to see when it's stable, when it's losing energy, when it's winning energy, etc. And so impedance control is a way to formalize and control the interaction with the environment or other agents, right? This is really something totally fundamental. And so when Hogan formulated impedance control, so in '84, the early '80s, then it was not yet clear to the people how important it is. But over the years, it became central to robotics, because robotics is interaction on the environment. And now the question is impedance control in humans. So how does it work? Or why is that something important? Of course, it's important because we have to interact with the world again, but also there's something that is specific to human, is that muscle are programmable springs. So muscle are intrinsically compliant. This is, as you know, contrasting to traditional robots. So I think this winter school is to look at alternative robots that are compliant. Human muscle, human body is compliant intrinsically. And so impedance control depends in human on muscle that you can program. You can change the stiffness of a muscle. And it depends also on the mechanical structure of the human body, so the posture you take. So for example, so if I'm like this, it's very rigid because of the singularity. If I'm like that, it's less rigid. Okay, so this is why impedance control, and so this gives the frame for this 2 hours lecture. And also the approach we use to model human motor control. So we use a system-level approach that considers both the biomechanic and the neural control, also the sensors, of course, the sensory receptors. And this I call human robotics, because it's like in robotics. In robotics, you have hardware, you have electronics, you have software, and the system is important. The complete system is important. And to study human motion control or motor control, it's the same. The body or the biomechanics in itself is important, but it's not all. And you have to consider also the neural control. If you consider the neural control alone, like a computer, it also doesn't work. You have to consider the biomechanics to see the effect of dynamics, of the muscle mechanics, and so on. So this is really important to consider both mechanical aspect and neural control aspect together. And in that way, so we develop physiological model that rely on measurable variables. So we do experiment and we do models that do not go beyond what we can measure, because if you go beyond what you can measure, you make predictions that you cannot test. So this is really important to keep model as simple as possible so that you're able to actually test in experiments. And you come to algorithms, and these algorithms then you can implement on robot, and this may sometimes give rise to novel behaviors for the robot. The recommended literature for that, so there is this book. We will basically, what we do is, if you want part of this book, or if you want to go further, you can look into this book. This is about neuromechanics. So neuromechanics, again, it's biomechanics and neural control together. And if you want to look at physiology itself, so you can go to this very, very big book. And the good thing of this book is that it's every chapter is self-contained. So you can pick one chapter, and you don't need to read the 1,000 other pages. And also, it's written for medical people, so it's relatively easy to understand from a scientific point of view. Technical aspects are covered by standard robotics and nonlinear control textbook. So this you can find in conventional textbook. And so some of the papers, so I cite some of the papers in the slide. You can look on that, or you can look at additional papers. By the way, if you want the PDF of the slide, I have it, I can pass you. And I think so the people of the school can also send you the link I have put on a server, and so you can get the slides if you want. Okay, so the outline of the presentation, so we will go first with muscle mechanics. After, we will go to single joint, so joint neuromechanics. After, we will go to multi-joint motor adaptation of movements, learning at muscle level with unstable dynamics, and then look into how it is going into robotics, so how you can implement similar adaptive strategies on robots. And finally, so looking further at algorithms, so learning algorithms. Okay, so muscle activation. So muscle is starting with works by the late 18th century, where people noticed that electric current causes muscle contraction. And this was important, of course, because before, people were not so sure what is actuating, what is commanding muscle. So at that time, people understand that muscle are activated, contract when you apply electricity, and so you can still measure electric current. So kind of estimate the motor command. So you place electrode on the muscle, and then you can estimate the motor command or the force that will be produced by the muscle. And so you can also use a robotic interface. You can measure the torque by the interaction and the displacement. So for example, this measurement, this is for width fluxion extension. So you have a haptic interface with a motor here, and you can measure the position, measure the interaction force, and also apply a force in order to disturb the system and see how the system is reacting. A main characteristic of muscle is that it's this. So if you input some electric current and at low frequency, then you get a full amplitude of the movement. If you put a higher frequency, then if you increase the frequency, so it's going further, faster, and finally you can try by yourself actually, you cannot change the position very much and very fast. So muscle actually are, from a robotics point of view, are a not so good actuator. So you can see that, so this is the low-pass filter that is characteristic of the muscle mechanics. And you see that the cutoff is about at 2 Hertz, and at about 4 Hertz, you have no signal going through. So this is determining the mechanics of the movement we can carry out. Another thing is, as I told you, I mean, it's obvious muscle are elastic. So you have elasticity in the muscle, and so you may want to measure, to estimate this elasticity. So how did people do that? So they take a muscle, not the whole arm, just a muscle of an animal, and you connect to a motor. And you have a force sensor, a position sensor, so you can change the length, you can apply a force, and you measure the tension. And you can make perturbations, so you make small perturbations. So in the case of this experiment, in fact, they did random position perturbations. They measure the resulting force, and from that, they deduce the stiffness and the damping. So you have a resistance to this perturbation that is characterized by stiffness and damping. And you see that, for example, so with the force, the stiffness is increasing. The stiffness is increasing with the force. That's something that is fundamental from muscle mechanics. And also when you increase the amplitude of the perturbation, then the stiffness is decreasing. All this is coming from internal mechanics of the muscle. I do not want to go into the detailed mechanism here, so you can find in books, but that's important to understand that stiffness is increasing with activation. That's the main property. The same for damping. Damping is also increasing with the force, and it is decreasing with the frequency of the perturbation. So it makes that, so for example, if you have a movement at the beginning or at the end of the movement, the damping is larger than in the middle of the movement. Yes?
You're talking all the time about passive muscles.
Sorry?
You are talking all the time about passive muscles, so not activated. Yeah. And only about muscle or muscle plus tendon structure?
Muscle plus tendon, but no reflex yet, for example. So just a muscle that is connected to a motor. Okay, let's summarize the muscle properties. So muscle tension increases with stretch and with activation. Muscle act like a low-pass filter with a cutoff frequency of about 2 Hertz. And a muscle have spring-like properties. That's what we will be most interested today. And stiffness and damping increase with activation. They increase about linearly with activation. Now, if we consider the system of a muscle and a tendon, then, so we see how we can calculate the stiffness or the compliance. So stiffness, by definition, this is the Hooke constant of a spring. So this is the derivative of the force by the position, right? And the compliance is just the converse, so it is the derivative of the position by the force. So if I have a force, how much a position does it make? So this is 1 over the stiffness. Okay, now if I have two elastic elements in series, for example, the tendon and a muscle, what happens? So then, of course, the lengths are additive, and the force here is the same than the force here, and the same than the force here, then you have always the same force. So when you compute the compliance of the whole system of these two elastic elements, so you have dx by df, and this is dx1 plus dx2 by df. Okay, and dx1 by df is equal to dx1 by df1, because the force is the same everywhere, the same for the second element, and then we get that the compliance of the whole system is the sum of the two compliances. So what that means is, if you have an elastic, a compliant tendon, you can stiffen your muscle as much as you want. It will not result in a stiff mechanism, right? That's something important. Okay. Now let's go to the sensor receptors. So to understand what kind of signal does the brain have to control movement. And so we see there are many sensors actually, but we concentrate on two sensors that have been studied extensively. These are muscle spindle and Golgi tendon organ. So Golgi tendon organ is between the muscle fibers and the tendon. And so it's basically measuring the force, or it's giving an estimation of the force. It's varying with the force. And the muscle spindle, so you have specialized muscle fibers that are equipped with muscle spindle, and the muscle spindle give an estimation of the position or of the velocity. So how we can see that? So let's see for the spindle. So we have a movement of the elbow. Okay, that's a movement of the elbow, and here you have that. So you have a motor. So the motor is moving your arm. So you should not resist. You do not make any voluntary contraction, as you see from the EMG. So the EMG is flat. There is no muscle contraction, and the robot is moving you. And then you put an electrode in the afferent, so in the nerves that is going from the spindle back to the brain, and then you get a signal here. And now in this part of the diagram, you do the movement yourself. Okay, you do the movement yourself. You have, of course, EMGs that correspond to the force you produce. And then you do a movement that is approximately the same. And what do you see? You see that the muscle spindle is producing about the same signal. So meaning that muscle spindle is giving some estimation of the position, or give a signal that is related to the position. In fact, it corresponds more to the velocities than to the position. One way to do that, to understand that, is that there is a procedure where you can vibrate muscle. You vibrate muscle and you close the eyes. You vibrate muscle here and you close the eyes, and then you have the impression that your arm is moving with constant speed. Why? Because the muscle are excited. So muscle give more or less a signal of velocity, right? Okay, anyway, is related to the position or to the velocity. So it's enabling you to understand what your body is doing. For the Golgi tendon organ, so to see what they do, so this is a finger movement, and in one case, so they just measured the movement, the finger, and after they put a load. And you see the difference. So with the load, the EMG is larger, and the afferent signal, so the signal to the brain from this Golgi tendon organ, is also similar to the EMG. And then you can conclude that the Golgi tendon organ give a signal that corresponds to the force or to the derivative of the force. Okay, so now we know the component. We know the intrinsic mechanics of muscle. So we know that it's elastic, that you have stiffness and damping, and the stiffness and damping increase linearly with the activation or with the force you produce. We know that the brain has at disposal some position and some force signal. So we can continue to look further the joint mechanics. So using, for example, such interfaces. So you have a motor here, you have a force sensor, you have the hand that is fixed rigidly, but not, so it doesn't hurt. And it is a support that is done in a way that you can measure EMG very well. And so it's a bit supported like that because the electrode you should put here. So if you put on a table, then you would have trouble to put the electrodes. And so in this case, it is in fact an interface for two wrists, so either bimanual or two people. And we, in fact, so this is our recent topics of research. We look how people interact physically, and we try to understand how they work physically. And we find that they consider the partner without even knowing that there is a partner. And so this is one experiment. So you see that, so you move here, and so you measure the position, you can measure the force, and everybody has his monitor. And in this case, so this is to separate the two and to make some interaction and to understand how they work together. But anyway, so you see this interface. You have, of course, the button to stop if anything is wrong. And you can isolate the two phonically, etc. Anyway, so this is a typical interface to study wrist movement, so one joint, wrist flexion extension. And of course, when you have one joint, you don't have only, so you have, what do you have? You have muscle on each side, so you have flexors and extensors. And you have several flexors and several extensors. And also you have reflexes. What are reflexes? So reflexes, this is basically neural feedback, right? This is just what the nervous system gets as feedback and what he's giving back. These are kind of dynamic system, a low-level dynamic system of the nervous system. So of course you know that you have spinal reflexes, so the fastest reflexes that just go to the spinal cord and back to the muscle. So, for example, this is this knee reflex. So when you hit here, then it's lengthening this muscle, and then it's going to the spine, and then it is contracting the extensor and relaxing the flexor, because you have connection in the spine that do that. And so these are spinal reflexes. Now you have a lot of other reflexes going to the brain and coming back. And all these reflexes combine, and so they have a latency of from maybe 40 or 30 milliseconds to 200 milliseconds or more. And why I mention these reflexes is that when you have stiffness or damping, then it's not immediate. I mean, the effect of an interaction is not just at one time. When you want to estimate it, when you want to measure it, you have to measure over 100 milliseconds or 200 milliseconds. And then you get not only the muscle properties, but you get the reflexes together. So the stiffness and damping, so this mechanical impedance, come both from muscle properties and also from reflexes. So these dynamic system properties of the low-level nervous system. How can we estimate the stiffness? So estimating the stiffness, so you have a robot and you disturb, right? So you disturb at the elbow. So in this case, so they do that, you do not, so this is undisturbed trajectory, the position, and they do a constant displacement here. They do a constant displacement. Because you have constant displacement, you have no modification of velocity in the middle, and no modification of acceleration also in the middle. And then you can see, okay, so if I do this displacement, what force does it make, right? I can measure the torque, okay? And then I can relate the torque with the displacement, and then I can divide the difference of torque by the difference of displacement, and I get an estimation of the stiffness. Okay, so this is a way to estimate the stiffness. And when you do so, again, you get not only muscle properties, but also reflexes coming together. And in fact, that's what you have. So when you interact with objects, when you manipulate, in fact, it does depend not only on muscle, but probably importantly on reflexes too. What is interesting is that, so you remember so if we look at one muscle, yeah, you remember in one muscle, stiffness is increasing linearly with the force. And what is interesting is that in one joint, it is also increasing about linearly. That's something interesting because, again, you don't have only the muscle, you have several muscles, and you have reflexes. And even then, you have about the same linear relationship with the force. So when you increase the force, when you increase the activation, the stiffness is increasing linearly. And what is even more interesting is for multi-joint movement, for multi-joint arm, you still have some linear relationship. So basically, the stiffness is increasing linearly with the torque. Now let's look at the elasticity of an antagonist muscle pair. So this is, so you have flexor and extensor, or like this, flexor and extensor. And so what does it make? So when you have, so this is something like that. So you have flexor and extensor. And then, so you have what is called the reciprocal activation. So this is the activation or the force, the torque that result from it. And you have also the torque that result from the other muscle. And the resulting torque is, of course, the difference of the two. So this is called the reciprocal activation. And you have also these areas that is the co-contraction, right? So you have reciprocal activation and co-contraction. And the interesting point is that the reciprocal activation makes a torque, and the co-contraction make basically the stiffness, okay, or the impedance in general. So let's look a bit into the detail mathematically. So if we have stiffness, we want to compute the stiffness. If we have elastic element in parallel, then the forces from here to here are additive in the two parts, and the distance, the change of distance is the same because they are in parallel. Or if you consider a flex and extensor, they are not equal, but if one is increasing, the other is decreasing of the same amount. Okay, so let's calculate the stiffness so together. So this is dF by dx, and you have the additive forces, so dF1 by dx plus dF2 by dx. and because the length is the same everywhere, so you have df1 by dx1 plus df2 by dx2. This is the sum of the stiffnesses. So not surprisingly, so when you have two muscles that act together at a joint, then the stiffness at the joint is additive of these two muscles, okay? So when you have elastic element in series, like for muscle and tendons, then the compliances are additive, and when you have muscle in parallel, then the stiffness is additive. Okay, and so let's compute the mechanics at the joint. So you have that the torque is equal to the moment arm. So the moment arm is quite important, time the muscle tension. Okay, this is the muscle tension. And you have that the length of the muscle is related to the joint angle also by the moment arm. So the moment arm is determining a lot the properties that you will have at the end point of the arm. It is like that. So it's important to know this moment arm, and basically by changing the moment arm, so by changing the configuration of the body, by changing the posture, you can modulate the properties at the end point. Okay, so so if we compute the stiffness at the joint level, so this is by definition the derivative of torque by joint angle. So this is rho times dn by dq, and this is finally rho square df by d lambda, so rho square times the muscle stiffness. So you see that the joint stiffness is related to the muscle stiffness by the moment arm at the square. And the same for the damping. And now, so let's look at the joint level. So you assume also that the stiffness is a linear function of the muscle force, that's what we have seen before. And then you get that basically what I told before, so the stiffness is the addition of the stiffness of the two muscles, and it corresponds to this muscle stiffness times the moment arm. And the torque is the difference of the muscle tension. And because the stiffness is a linear function of the muscle tension, we have basically that the stiffness is the addition of the muscle tension, or the activation, and the torque is the difference. Okay? Why it is important, it means that basically, so if you have a system of two muscles, then you can change the torque and the stiffness independently. If you have only one muscle, you cannot change independently. When you change the torque, it is changing the stiffness, or when you change the stiffness, it is changing the torque. It is not independent. You have a linear relationship for one muscle. But when you come to antagonist muscles, so at a joint, you can, in principle, change both the force, so the torque, and the stiffness, or the impedance, independently. And this independent control of stiffness, this is impedance control, right? That you can change the impedance by changing the force of one muscle. It is not impedance control, it's just muscle property. But that you can change separately, this is impedance control. Okay? Any questions so far? Yeah, by the way, as your colleague did, you can cut me at any time if you have any question. We don't have to follow a timing. We can spend half an hour on one slide if you want. Motor adaptation. I want to speak about motor adaptation because it is something so fundamental in human. And this is something that what robots should be equipped with. And it's starting. So let's consider the problem of a robot. So the robot has to move with his actuator, with limited knowledge about the body, about the environment. You cannot know, you cannot model, it doesn't make sense to model any environment, right? You would have to do experiment to model any environment. So, and the robot has to constantly perform new tasks in changing conditions. So again, you cannot have a model of every new environment and every new situation. So the only way to go is to get information about the movement, robot have sensors, and to learn, right? To learn appropriate action according to the sensor information you get from all your sensors. And this is actually exactly the same problems that a human has, right? A human has to perform new action every day, and we have a lot of sensors, probably many more than a robot. And with these sensors, we have to connect to the action, to see what happens, and to make sense of all this. And this is motor learning. We have to make sense about the experience we get about our actions. So we do some action and sense and see what happens, and from that we conclude and can go further. And this is motor learning. And again, in human, you have that really fundamentally at every level, not only for children, also for adults. Also, if you age, you change your control with the changing properties of your sensors, for example, of your muscle, etc. Robots don't have that, and should. If we want robots to be able to act in a flexible way, to become versatile and as biological agents are, then we need to develop learning for the robot. Okay, humans also need to adapt because you have very long reflex delay. And because you have very long reflex delay, you have to prepare the movement. It's not fine. So consider what a baby is doing. So a baby, so when there is an object, is going so basically in feedback mode, right? So looking what the action is doing and coming closer. And by about 6 months, babies start to understand, okay, so I have to do that. I can make a full movement. So they start to develop this feed forward, this model, and such. So they start to, in a way, get rid of the sensory delay. How do we investigate? So we have robots like that. So this was a robot we used in Japan, but now you have such robots everywhere. We have some in London also. So this is switching movement. So the movement you do to take a glass, for example. Yeah, so you have big motors, you have force sensor, and so you can measure the force, you can measure the position, etc. And so this is a typical experiment. So you do free movement like that. After you put a force field like that is a linear function of the speed. So you have zero force here, zero force at the end of the movement, and you have a force that is proportional to the speed. And that is pushing you to the left, basically. And what happens then is that, so of course, because it's pushing you, then first you are deviated to the left. But after some trial, you learn to compensate for this force. And this is, so you perform movements that are similar to free movement. And if you take out the force field, you don't know, you have learned, and you take out the force field, then you have trajectories. So you apply a force in and it's moving you to the other direction. It's like if I lean on a wall and you take out the walls, and I will fall, right? That's the same. And so we can see the evolution of the error here. So the error is decreasing very fast, and you have this after effect. So if you take out the force field, then it's going to the other direction. And you see the evolution of the trajectory. So 1, 2, 3, 4, 5, etc. So it's going gradually to the straight line. And this is the force before learning, the lateral force before learning and after learning. And basically, you have identified the force field. Okay, and this you can model that with this simple model. So you have muscle mechanics, you have muscle viscoelasticity. So this is muscle mechanics. You have neural feedback here that is delayed, and you have, of course, interaction with the environment. And what you have is that you build a feed-forward model of the task dynamics, right? So you learn to lean on the wall. And so you can learn, for example, with any mapping from the planned movement to the motor command, for example, in neural network, or basically any mapping. And let's see how this learning is working. So for one single trajectory. So for one single trajectory, at the beginning, you assume you have no feed forward. You don't know you have no force, no lateral force. And then you do a movement with the arm or with a robot, and you get some feedback, right? I mean, you have a linear controller, a PD controller, you have a linear controller, and then you do the movement with this linear controller, you get some torque. And this torque corresponds roughly to the dynamics of the task. So you can use this as feed-forward next time. But because it doesn't correspond exactly to the dynamics of this task, for example, you have sensory delays and you have a slightly different trajectory, then you incorporate only a bit, so half, let's say, of this feedback. You incorporate as feed-forward. And then the next time you do this movement, then because you have this feed-forward, the feedback is smaller. And so you build up the feed-forward, and the feedback is going down. And finally, you have only the feedbacks that correspond to stabilization, and to unmodeled dynamics, so what is not reproducible. So this is this learning law, and so with that, so you can, for example, implement on robots. So this is iterative control in robot. So that's what we did long time ago with this small parallel robot, and you see that the error is decreasing, and you see that after learning, the feedback is reduced to very, very little, almost nothing, right? And so this is on another robot, a big robot that is taking about all from here to the wall here. Very dangerous machine. So a robot with 3 wheels and 2 motors by wheel, and you have, so it's supposed to carry a milling machine, so it has to be very accurate, and so you want to learn the dynamics. And then you can learn the dynamics by making gymnastics. The robot is doing gymnastics and learning to decrease the feedback. So identifying the parameters of the model, of the dynamics to minimize the feedback. And then after about 1 minute, you have learned, and then you can move very accurately. And so this kind of model works also for humans. So we have free movement, we have this learning that we see in the data, and you get similar learning in the simulation with this iterative control, with this adaptive control. So you can learn to compensate for the external force. Okay, so I will not go too much about the summary. I think we want to continue. So we want to continue on the learning of more realistic tasks. So why more realistic? So let me jump first. Yeah, so more realistic tasks. So every time you have a tool, so can be a screwdriver, can be the fork, can be the knife, you have to learn to compensate for instability. If you have a screwdriver, it can fall on one side or the other. And you know what it is with instability. So instability, normally it would stay here, but because in any physical system you always have some noise and it's falling to one side or the other. This is instability. And basically every time you have a tool, and you have a tool for most action, every time you have a tool, you have an unstable interaction. So for example, think of drilling. So this you have experience. It's very difficult to drill, to keep. It's going further. And then, but the point is that you can learn. You can learn to deal with this instability, right? And so we wanted to understand why you can learn, how you can learn to deal with this instability. And strangely, this is also something that robots didn't have. Why? It's not very clear, but probably because previous industrial robots are so powerful. They are never unstable. They just break the table if they have to do something, right? But when you come to soft robot, to light robot that we start to have nowadays, then you have this instability coming with the interaction, and also you have interaction with human, and then you cannot be too strong, and then you have to deal with it, instability and understand how to deal with it. So maybe we can learn from the human. So to consider that, so when you have instability, so it's about interaction, it's about impedance, right? So what is my impedance? How can I change? How can I model the impedance? So impedance, so mechanical impedance, so this is the generalization of viscoelasticity in one muscle. So mechanical impedance, so you can consider, so this is, by definition, the resistance to perturbation. And if you make a linearization, you can interpret this as inertia, damping, and stiffness. So this is mechanical impedance. And to visualize stiffness, for example, we can use so-called stiffness ellipses. So what is that? So you make a perturbation in all directions, and you measure the restoring force. So when you disturb, it tends to come back. So you measure the restoring force. And you see that the restoring force actually is not the same in all directions, and it doesn't have to be opposed to the perturbation. If you do a perturbation in that direction, it can be then the restoring force is in another direction. In general, that's what happens. Anyway, so you make a perturbation of the same amount in all directions, you record the restoring force, and you plot this as an ellipse. And you see that, so you have, for example, here's the direction of minimum stiffness, and here's the direction of maximum stiffness. So you get a visualization of the geometry of the stiffness. And this stiffness depends on the posture. So the geometry of the stiffness depends on the posture. That's what you see in this data from Perrault. So you see, so this is inertia, viscosity, and stiffness. Of course, the inertia doesn't change with, sorry, I didn't tell everything. So here what happens in this experiment is that you apply a force. You apply different level of force in 4 directions. So in this direction, in that direction, in this or that. And when you do that, you see that the stiffness, again, is increasing with the force you apply, okay? It's increasing about linearly. The viscosity is also increasing, not exactly linearly, a bit like a square root. And the inertia, of course, doesn't change with the force you apply. The inertia is due to the body, the limb, right? About the rigid body dynamics. Okay, so anyway, so you see that the stiffness is changing with the posture. And it is something important because if you want to change the stiffness, you can change the posture. And the question is whether we do that. So we humans, do we change the posture to have the correct impedance? To see that, again, Perrault did an experiment. So you have a robot, and the robot is disturbing you. And first, the robot is disturbing you in this direction. And so the subject can explore the posture, so see where it is more comfortable. And they find that, so basically, when you have a disturbance, the more comfortable is something like that. And afterwards, a posteriori, yeah, it's not so surprising because you use the singularity to oppose the disturbance. And if you have a disturbance in that direction, then the most comfortable posture is this one. Again, that's a singularity. And if you have disturbance in that position, along the z-axis, then you put something like that. Again, it's a comfortable position where you use the mechanics to produce the stiffness, okay? So we can change the stiffness by changing the posture. But can we change the stiffness also by changing the muscle contraction, by coordinating the muscle? That's the question we look into. So to look whether we can change the stiffness, so we produce a force field with the robot. We produce a force field that is basically negative stiffness. So what is negative stiffness doing? So this is something like that. So you have a small force here, and when you go far from the straight line, you have a larger force. So basically, it's sliding to the right or sliding to the left. If you're a bit to the right, it's sliding to the right, and if you're a bit left, it's sliding to the left. And you cannot control. It's unstable. Why is that unstable? I mean, it's unstable, that's a force field, but why is that a problem? It's a problem because you have motion variability. You have always some variability in the movement. And then sometimes you will be right and sometimes you will be left, and you cannot really control. And then it means that sometimes your hand will go here and sometimes it will go there, and you cannot control that. And this is what is happening. So it's going away. I mean, it's going away, and you cannot control, and you have the impression you will never learn. And so you have the impression, so it's going right, it's going left, right, left, and you cannot control. But after about 100 trials, then slowly you start to learn something, and then you can do movements that are similar to free movement. So whether the disturbance is like this or like that or like this, then you are able to compensate for this disturbance. And how do you do that? I mean, so when we found that, we know as people increase stiffness, right? Because you have negative stiffness, so, and you know that when you contract muscle, you can increase stiffness, so we thought, okay, people increase stiffness. But what we thought is that people increase stiffness in all muscle of the same amount, because this would be simple for the brain. And what we found is something very different. People increase stiffness exactly in the direction they need to increase to. So for example, when you have lateral destabilization, then you increase only in that direction. And when you have destabilization like this, then you increase along this axis, the blue ellipses. Or when you have disturbance like this, then you increase only along this direction. And so for this direction, it means, so lateral perturbation, I use both the shoulder and the elbow. When I have a disturbance like this, then I use basically more the elbow. And when I have a disturbance like that, I use mainly the shoulder. In all cases, the subject are able to compensate exactly the destabilization. It means that they pick up exactly the muscle that are required to produce the stabilization. Okay, and that's something that we found strange, that the brain would be so clever to pick up the right muscle at the right time. And so that's why we developed model to understand how the brain could be that clever. And we found also that, so if you have, so this is the experiment. So if you increase the level of destabilization, you see that the people will increase the compensation of the stiffness in a linear way to keep the same stability margin, right? They keep the same stability margin. They learn to keep the same stability margin. And we find, yeah, so we have a model I will show you after that is predicting the same. And so it seems that, so the brain is able to pick up the right muscle and does it to keep the same stability margin. And so this may be important for the brain because it means that whatever dynamic environment you have, you will learn to compensate for this environment, and after a short time, you have the same condition, and then the brain, the higher level of the planning can be done on the basis of free movement. So whatever interaction you have, you compensate for it, and then the brain can plan always the same on the top of that. So what is this model we found? We look at how the muscle activation is changing as a function of the error. And we see, so changing from one trial to the next. So we measure EMG, and we see how it is changing from one trial to the next. And we see that we have this kind of V-shaped function. And how does it work? So if you have a flexor and an extensor, if you deviate to the right, then after the flexor will increase more than the extensor. And then you get a change of torque, right, from the difference of the activation. And this is iterative control. Now, what is interesting is that because you have muscle mechanics, when you increase the activation, it is increasing the stiffness. And after you go to the left, and you have again increase of stiffness. And then you build up co-contraction. So you tune the force and you build up co-contraction so that you get higher gain, if you want, of your controller, so you get a better control. And when you get a better control, you get less error, so you come here, and where you have less error, then you have a decrease of co-activation. So the controller is working by a concurrent minimization of error on the one hand and of effort on the other hand. And then by minimizing both error and effort at the same time, you get the model, you get the adaptation. And you get correct prediction, so whether you have a force field that is just deviating to the left, so you have a gradual adaptation, or a non-stable force field that is completely, so that lead to complete divergent trajectories, then the simulation is predicting what you find in experiment. You get also the correct stiffness prediction. Okay, so yeah, so we thought from the experiment we have something that is very clever. We have that the brain is very clever, and we find a very, very simple. So these simple systems that you put in every joint or in every motor neuron, and then it seems that the brain is not so clever. It's very simple and it's working totally automatically. Okay, so you can also predict the evolution of muscle activation trial after trial, and you see so in the shoulder muscle, biarticular muscle, elbow muscle for unstable force field or stable interaction, and you see that the model is predicting well what is happening. Note that the curves do not have to match exactly because both the human and the model have stochastic, so every time it's different. Every time you do some learning, it's different, and every time the simulation is learning, it's different. Okay, so you have prediction of the experiment with the simulation. It's coming well. So this is what you have. So by having this simple V-shaped function, you can and minimization of error and effort, then you can get the adaptation that you see in the data. Any question? Yeah.
In all experiments, the participant was looking at the target, right? In all the experiments, they were vision guided. They were looking at the target to decide where to go.
Yes. You get the same result if you actually you don't have to look at the target always. Actually, you don't have to look at your hand. So we did the same experiment if you see the target and you do the movement and you see where your hand is coming, and it's coming to the same result. You don't have to see your hand.
They stopped
see the
looking
target.
after the initial
You
movement.
see the target, whether you see your hand or not, it doesn't change.
Very surprising.
You have to see where your hand is coming from. After you have finished the movement, you have to see where it's coming, whether it's completely here or here. But you don't have to really see during the movement where it is. Any other questions?
What happens if the use of freedom of the movement must the use of freedom of the movement must
So, yeah.
I don't mind for the questions, but
Yeah. Yeah, anyway. Oh, good. Fantastic. Yeah, then I should have used from the beginning because I wouldn't have to keep here all the time. Yeah.
you stay at the
Yeah, thank you very much. Hello?
What happens if the use of the freedom of the movement drastically increases? For instance, if you do like a very fine and precise finger movement, like just like playing piano or whatever, and does the same laws apply for this kind of movements? Because the examples that you give is like a total use of freedom and then relatively simple.
Thank you. So I would bet yes, but I don't know. I mean, the point of the experiment is that it's difficult to make some things that way you can really interpret very clearly what is happening. So that's why we were strict on use of movement. I guess it would be the same, but I cannot know for sure. So basically, we think that you have something that's not only at every joint, but in every muscle, or perhaps in every motor neuron. And this V-shaped line of behavior would be everywhere. And this V-shaped line of behavior is something very simple that would really be nuanced, because what it has is so you have compensation of error, and this, we have signal like that in the third element, for example. And this relaxation, so this increase of activity, would just be kind of every neuron will lose a bit of its value every time. We forget. This would be like a forgetting of consider is that this is happening totally automatically and involuntarily. So, for example, I know this algorithm. If I try to do the converse of the algorithm, I cannot come against. So I have to do it. It's totally automatic, and I cannot disconnect it. Any other question?
So you showed us that the brain is able to learn the disturbances that affect the task. But we know in control that there is a difference between having a model of the external disturbances or not. So were your subjects aware of what kind of force field they were facing or not? The task was completely blind. They just had to learn from experience. Or you informed them that they were facing like an unstable force field to the left or to the right. Is it clear? Okay, so you just, I didn't understand if you just gave the task to the subjects, or you informed them that they were going to face a force field that was pushing them in one direction or in another, or just in one direction.
So the only thing you tell them is that they have to go to the target, and they have to do it in some time. Because of course, if they would be very, very, very slowly, then you would not have you would really keep the data like this. So it has to go relatively fast, and they have to go to the target, and you don't tell anything about the force field. Now, even if you would tell them something, it would not shrink. So for example, I know exactly of course what I put in the experiment, but my results are not different from the results of anybody else. So first I thought I cannot consider myself as a subject because I know what I want to do. But again, it's totally automatic. So we have a lot of automatic stuff, much more than we think. We have much less voluntary stuff. You know, it's like more if you justify after, or your brain is justifying after what is happening, but you just do this.
From the several plots that you showed, I could see that you had to stiffen your muscle to contract or to reject the disturbance along the direction where the disturbance comes. Or in order to maintain the stability margin, you had to increase the stiffness. Is there any case that you can use soften to maintain the stability margin? Or can you also use the damping instead of the stiffness? Yeah.
We'll show you an experiment after. Okay, what I think, I never tried this force field, but so people have tried a force field to the left or to the right at the same time, and basically this doesn't work. On the other hand, if you make one force field to the left for this movement and one force field to the right for this movement, then this you can. Or if you, so people have tried something like that you. So you have a force field to the left when you do this, and a force field to the right when you do only this one hand. And then it's working. So you have to associate to a different single movement. At time you can learn two force field at a time. But otherwise you cannot learn two force field at a time. But you can learn one after the other. This you can. And for the learning, this is something probably like the bicycle. You learn once and then you can always do it. So for example, this unstable force field, I have learned this, and so that was experiment I was doing in Japan, and I was in Singapore at that time, so I would sometimes go for a few weeks. And then a few months later, I would go again. And then one time, I was doing the experiment, and I let my colleague put a stronger force field, then he's putting the stronger force field. And after 5 minutes, I was tired. What that means is that I didn't become humble, but I had learned. I know what to do, but I didn't become strong. So it is something you really learn. And even now, I know how to do. I cannot explain exactly what I do, but I know how to do. It's like that. One thing to consider is that so you can learn to compensate for the force, to compensate for instability, but you cannot say, so if I ask you, compensate for this instability, you cannot. I cannot know that. I can learn to compensate for something, but I cannot know explicitly what that is. Anybody? Otherwise, we continue. Okay. Okay, so learning of a robot, right? So if I manage to, the video doesn't want to go. Voilà. Okay, so instability and still unstable. So repeating. Okay, so it has learned. So what we did is basically, so you have a trajectory and we put stiffness and force adaptation according to this V-shaped function. We put in the robot, and that's what we learned. So it's, yeah, we can think that it is similar to the interaction human learn. So if we look at so we did an analysis of this controller, so using Lyapunov analysis, Lyapunov theory. And so how does a controller really look? So what you have is, like in humans, so you have the basis for free movement. So this is a linear controller for free movement, right? This is a linear controller. That's what you have. And on the top of that, you learn to compensate for the force of the interaction and to compensate for the impedance of the interaction. Okay? So you learn the force, you learn the impedance. And this is, so again, so this is the basis linear controller, and on the top of that you learn nonlinear force and impedance and linear impedance. And so this is this learning law. So it's again very similar to this V-shaped function. So you increase the stiffness with the error, and you tend to decrease all the time. So minimization of effort and minimization of error at the same time. The same for the damping. And for the torque, it is also the same. And so we can see what happens also on this robot. So you put a load, and then you have interaction. So you see, so you have undershoot, of course, because you have the load, and then the robot is starting to compensate. So at every trial, it's compensating more, better, and you see, so it's the amplitude is increasing again, and then so now it has increased. Oh, sorry. Okay, so now, so it has learned, it has fully compensated. Then you take the loads and you have overshoot, of course. So you have overshoots. And then again you compensate for this overshoot. And then he's testing the stability, the robustness of the controller to perturbation. Again. Yeah, so we see that the learning has not been disturbed. So the learning is robust to perturbation. Yeah, so that, okay, so you see that, so the learning is, so you see how the learning is working. What is interesting is to analyze what is haptic. So you have, okay, so you have, now you put the load, then you have undershoot, and it's adapting, and you take out the load, and you have overshoot, and it's adapting. But you have not only that, you have at the same time adaptation of impedance. So every time, basically, you have an unexpected situation, then the stiffness is increasing. Okay, the stiffness is increasing, and so here it is increasing, and then it's tend to decrease, and you have again an unexpected situation, and it's increasing again. So you have really adaptation both of impedance and force at the same time. This is something really completely different from previous adaptive controllers. So another task with a redundant robot. So we have 7 degrees of freedom, one V-shaped function, one pair of V-shaped function in each joint, and so you have to keep the position. It's compliant, and then you see that when you disturb in a direction, then it's become stiff in this direction and keeping compliant in the other direction. Okay, and it's like in humans. So if you disturb my arm, then I don't need to stiffen the body because I have inertia, it doesn't move. So I just contract the muscle that I need to contract and no other muscle. And that's a bit what the robot is doing. It's stiffening exactly where it needs to be and not elsewhere. So let's analyze a bit in detail. So we have position, force, stiffness. So when you apply a force, so it is only one joint, then you have compensation of the force, no change of stiffness, no change of trajectory. Again, the same. Now, high frequency perturbation, you see that only the stiffness is increasing and not the force. Right? It's happening automatically via the 3 parameters of this controller. No if, then in the adaptation, it's just through these 3 parameters. And now, okay, now what happens is that you apply a long force. So it's like if you have a goal here and you have a table, and then you would increase and maybe break the table or the arm. But now you make that the reference trajectory is coming to you a bit, so you see that the force, so the position is changing, coming to you, and the force is decreasing. You avoid too high force. And around the new posture, then you have similar impedance adaptation properties if it has to be. And if you let like that, then the reference slowly is coming back. So if you let free, it's coming back to the absolute reference. Okay. Now the same controller, so we have adaptation of position and adaptation of stiffness, and we can make that, so what we did here, we put the reference below the surface. So here, so you have the surface, we just put the reference a bit below. And the robot doesn't know the geometry at all and doesn't know the surface, right? It doesn't know whether you have a lot of resistance or not in the surface. And so you scan this surface, you scan it like that. We have a force sensor here, but we don't use the force sensor. It's making kind of force sensing, force control. I mean, the force is basically always the same amount.
It's better if you use the other one.
I think that.
Yeah, probably.
Okay, sorry. So the force, it's making some kind of force control without using the force signal. In fact, it's like an observer that is identifying the surface. Okay, so now we have scanned the surface. So let's see what we get. Sorry. So what we get is, so we get both the geometry, right? And we get also the stiffness. What is the stiffness? It is the resistance to the movement. So for example, you have more resistance where you have this macro Velcro here. So you have more resistance and less here. And you see that the endpoint force is always remaining at the same level. So you have really kind of force control, but without force sensor. And you have identification of both the geometry and the resistance to the movement. So what is this resistance to the movement? It's kind of characterization of the structure of the surface. So for example, if you have Velcro, you have larger resistance than if you have something like this table, right? And so these are different kind of surfaces that you can identify also in that way. Okay, another task that could be useful, so cutting, right? So something, not only abstract tasks, but now concrete tasks that are useful for robot. So consider styrofoam. You know very well from daily experience, it's very difficult to cut styrofoam. So we ask the robot to cut with a knife almost vertically, so that it's especially difficult. And we colored the styrofoam in black so that you can see what happens. And what happens is if you have adaptive, we use our controller, then you have adaptation of impedance, then it's cutting smoothly. On the other hand, if you have rigid stiffness, it's not cutting smoothly. And of course, you could say, okay, so if I can just take the value that is learned and put it as rigid value and it will work fine. Yes, of course. However, if you have a material of changing properties, you cannot do that, right? That's the point. And also, it's a method just to learn the correct value. So it can adapt to different materials and cut better. Another example of this intrinsically unstable task, so you see that if you have drilling with a fixed impedance and the hole is larger than with adaptive impedance, and so this is without and this is with adaptation, and you see that the hole is better. Okay, so this is this algorithm of human motor adaptation, so with minimization of instability, error, and effort at the same time. We're using 3 parameters for this V-shaped function. And this is the first model able to explain unstable mechanical interaction typical of tool use. We have generalization to movement in the redundant body and muscle system, and we can use it to model healthy and pathological motor control. And on the robotic side, this is the first controller for adaptation of force, impedance, and trajectory. And so this is able to handle different tooling tasks, inducing instability, as humans do, and it does not require knowledge of shape of the tool object or the surface texture. And finally, it's good to utilize it's good for variable impedance actuators. So you have, for example, this experiment that was done several years ago now at DLS with a variable impedance actuator, and the same experiment we did before, and it also is working fine. So these variable impedance actuators, so you have basically 2 motors by axis, so you need one motor to tune the stiffness. That's what you see here. Any question here? Otherwise, I show you this thing, so you can use this human-like controller. For example, if you have a bimanual training, so for rehabilitation, so you have bimanual training, so the good hand is training the bad hand. And what you do is that you put this human-like controller to tune the assistance of the good hand to the bad hand. And the point is that the bad hand should learn as much as possible. If you drive the bad hand all the time, the bad hand will not learn anything. So you put this human-like algorithm in the connection from the good hand to the bad hand. And because this algorithm is minimizing efforts, so it's making that if the good hand can do the job by itself, then the bad hand can do the job by itself, the good hand will decrease assistance. The good hand will not help if the bad hand can do. If the bad hand cannot do, the good hand will help. So you see that the overall force produced by the good hand is decreasing with the trial, and also the actual trajectory at the beginning. The stroke patients, they can move only a little bit, and they learn to increase the movement. So with this adaptive controller. So this is what we have done. So we did experiment with these robots on human motor control, and we got knowledge about human motor control. And then we did derive a biomimetic algorithm on the human motor learning, and then we can use it, for example, to tune assistance of rehabilitation robots. So that's what we can do, this approach of human motor control and robotics and back to the human. And finally, so I will finish on the learning and generalization. So how does generalization work? So now, before we have seen always one movement, right? We have seen the learning of one movement, or it was only one axis. So what happens when you have several movements? So coming a bit to the question you had asked before. So what you want to do is, so you want to learn several movements. So you want to learn a force field in every movement. So how can you do that? So what you can do, so you have the same learning controller, but you have a mapping from the planned movement to the motor command, and you will learn this mapping that should be valid for all kind of movement. So how you do that? So you have that the motor command is a neural network of the inputs. So you have the state. The state is coming to nonlinear functions, so Gaussian, and then so you have your input space. So on your input space you have some Gaussian, right? You cover your input space with some Gaussian, and the Gaussian combined linearly. So you have a sum of Gaussian, and this is what this matrix is expressing. So these are linear components that multiply this Gaussian. Okay. So if you have to learn a function, then you have this Gaussian, and then you have to learn this weight of the W matrix to combine this Gaussian into this volume. And the advantage of this is that you don't need any physical model. You don't know the interaction a priori, so you have to have a model, so this neural network that can learn almost any function. So this is this Gaussian, this is how they combine linearly. So if you have the input space, so you cover your input space with this Gaussian. So you see this Gaussian covering the input space. And then, so you have the same algorithm before, so we have minimization of error and effort again, and you have to translate this, so this is minimization of error here, and this is minimization of effort, so this is this W matrix component, right? And then if we minimize as before, so error and effort, we come to this adaptation of the weight of this neural network. So this adaptation, so each component of this weight matrix is, so you increase it by a term that is multiplying the error and the feed forward, and here you have, so this is minimization of error, and this is minimization of effort, like before. This is, again, this V-shaped function in the space determined by the neural network. And now with that, we want to see whether you can learn several movements, so to generalize, so you learn on a movement and you see what is transferred on another movement. So this is related to this experiment that was done by Condit and Musaivaldi in 1997. So what you want to do is you have two populations. So it's a population learning to this force field on a circle, and the population learning this force field on straight line, okay? Straight line movement with this force field, or circular movement with this force field. So how does it work? So if you learn to perform movement on the circle, so free condition, you make a circle, no problem. After you put this force field, you see that the movements are deformed by the force field, of course. And then you learn, so you continue to do circle, you have to do circle, you continue to see, okay, so I'm doing this, I have to do a circle. Then you learn, and you see that you become able to do circular movement like in the free condition. And if you take out the force field, you see that you have after effects, so the trajectory is deformed in the opposite ways than the first time you put in the force field, like before. So this is one population, okay? Turning, so they train on a circle. Now you take another population, they learn this force field only on straight line movement, okay? Movement from here to one of these 8 targets. And then, so they learn in this force field, and after you test them on the circle, they have never done a circle before. So they test on the circle with the force field, they have learned the force field in the straight line movement, and they don't know the condition. And what happens, so you see that after having learned in this movement, they transfer very well to the circle, so they have similar good circle as people who have trained on the circle. And if you test when there is no force field, you find similar after effect from the transfer of learning this straight line movement to circular movement. So you see that you have generalization. So the people who train in this movement, they learn a force field along this straight line movement, they can transfer to circular movement. And so we have simulated this experiment with our model, and we find the same. So free condition, first trial, and after learning, and after effect. And if you train the same neural network on straight line movement, you see that when you transfer to circular movement, it's about a circle, and it is, in any case, much flatter when you have the after effect. So you have generalization. So with this with this model, if you take channel mapping, like a neural network, then you can get generalization of the learning on other movement types. And finally, coming to your question a bit, so we did an experiment where you have unstable force field in two movement direction, and you learn at the same time. You learn, so this movement with instability and that movement is instability, random, sometimes this, sometimes this. And you see, so the experiment, so this initial trial and after learning, so you're able to compensate for both. And what you do is that you learn stiffness that is specific to the movement direction. Okay, you increase stiffness specifically to the condition of your movement. And again, we can simulate this with our model, and we find the same direction-specific compensation of instability. Okay, so this is what we have learned. So the nervous system automatically learns to coordinate muscle in order to compensate for the interaction forces and stability. So we can learn to compensate for instability. We can learn to produce a correct impedance. And we have models that by an adaptive, we have models that by an adaptive controller that is able to predict the evolution of muscle activation trial after trial. And what is important is a muscle has spring-like actuators with tunable mechanical impedance. If you have only one muscle, impedance increases with activation and force. However, the nervous system can control impedance independently from force by combining several muscles acting at a joint. Okay? And on the robot side, we could make a model-free controller for adaptation of force, impedance, and trajectory. And we developed the algorithm, we analyzed its dynamic properties, and we demonstrated with this experiment, and this is a robot controller that can be used on any robot, especially for soft robots, so that can be flexible or more stiff. Okay, I think that's about that. So I'm available for your question, if any. Yeah.
I'm interested in the example of the robot drilling. So you mentioned that the basic control method is at every trial you take the environment forces and not them as the feed-forward model. But at every trial the drilling environment force will be different. So how does it make a better drilling action?
So if you change the force field at the time.
No, I'm not talking about the force field. I'm talking about the drilling example where the robot did a drill into a piece of material, and regular position control made a large hole, and
that's very simple. So what happens is, so if you have variability, then it will increase the stiffness of the material from this reshape function. And then, it's increasing the stiffness, and then if you have higher gains, then you have less stiffness.
how many times
The force of the wheel remains the same. However, the tendency to tremble of the machine is the same. However, you have guidance. You have guidance with
lightweight arm used in that experiment? KUKA lightweight arm.
That was a book.
But that one doesn't have the two actuators per joint. There's only one actuator per joint. So you cannot control independently the position of the that true?
That's a new one.
It's only one motor per joint. Yeah, does it have two motors per joint?
No, I mean, as you know, okay, so the whole robotics and organ and everybody did impedance control resolved by a hard actuator and to change the gain of the controller. So it changes the gain of the controller. So it increases the stiffness of the controller, decreasing.
What exactly was the learning step in this drilling?
Yeah, so what is happening is that you have a controller that is a linear controller. And on the top of that, you learn to compensate for the force or to compensate for stability. So it can make the controllers differ.
And measurement was in position. The error which was compensated
Yeah,
for
you
in
want
position.
to add stiffness so you have a default value for free movement. You have a default value for free movement, and when you come to traction, it may increase or not, depending on what is required.
Yeah.
Yeah. Yeah, you have two parameters.
Yeah, and how do you choose them? That's possible to look at how humans choose these games.
Okay, so we know ideas by human. I mean, we know that. So basically, of course, what is happening is that. So basically, you have these three parameters. So you have the parameter that is making the adaptation of force, and you have the parameter that is making the increase of impedance, and you have the parameter that is making the decrease of impedance. And in human, what it is that you learn the force first, you know, go faster, and after you have adaptation of impedance. So and of course that's a logical way, because if you would adapt the force all the time, you would not have any adaptation of impedance. All the force would make the work. So that's what we find in human. Now what we want to do is the same, that you have first adaptation of force while you have stiffening, and after you have slow reaction. Now exactly the parameter we take, it will depend on the application. And so right now we do pragmatically, but so we are working now on finding systematic how this learning parameters should be selected. That's something that we don't have yet. It will depend. So it will depend on the application. Right? It will depend on the task. So we want to find how it depends.
How does it differ between different subjects? I have just another question. So in the experiment you showed us that, let's say, the one is unstable, that the hand needs to move from one position to this one in a
if you let the subject do the movement very, very slow, then of course you will not see that. But if you ask the subject to be fast enough, then you say it's indicator. We constrain the movement time a bit. Why I say a bit is that basically we are very bad at making movement at some duration. So if I cannot really constrain you to make a movement of 600 milliseconds. So what we do is that so we have a target of 600 milliseconds, and if the subject does a movement that is too fast, so less than 500 milliseconds, we indicate after the trial that it goes too fast. And if you have a movement that is more than 700 milliseconds, we tell it too slow. The only thing, actually, it does not so matter the time duration, but we just wanted that the time doesn't drift systematically. That's why we constrain a bit, but we cannot constrain it really. We are very bad at planning the time. Any questions?
Thank you, Etienne.
So there's a break? There is a break now?
Yes.
Yeah, there is a break in the room, the usual room.
If you have other questions, I'm available during the break as well. Okay. Voilà. Yeah, this I have to give.